For Module 3, Lesson 22 problem set, we're going to go through the concepts of prime or composite numbers. And prime and composite numbers is not a very challenging concept once you know it, but these are probably two brand new vocabulary words to you. When looking at how numbers interact with each other, specifically with multiplication and division, if a number has one pair of multiplication facts to get to a product, that is what's known as a prime number. And if it has more than one pair, then that's known as a composite. So in our example, we have 4, and we can recognize that we have the pairing of 1 times 4 to get to 4. We also have a pairing of 2 times 2 that also gets you to 4. So since we have two separate pairs, this would be a composite number. And our factors would be 1, 2, 2, and 4, but since it's 2 times 2, we don't need to repeat the second 2. Let's look at B. It says 6. So I know 1 times any number is always going to be that number, okay? And that's going to happen regardless of the number. But the question is, are there any others that I can multiply with whole numbers to get to that whole amount? In this case, I can multiply 2 times 3 or 3 times 2 to get to 6 as well, which means 1, 6, 2, and 3 are all factors of 6. But we like to put it in numerical order. So 1, 2, 3, and 6. Since it is more than two numbers or one pair, it is composite. In our next one, we have 1 times 7, and unfortunately, there's nothing else that you can multiply to get to 7. I mean, you could do 2 times 3.5, but we're looking at whole numbers. Since there's only one pairing that equals 7, and the factors are 1 and 7, we call that a prime number, okay? It has to have more than one pairing, okay? I'm going to move down to a larger one. For instance, we have 1 times 16. We have 2 times 8. We have 4 times 4, okay? It doesn't matter if I have 2 or 3 or 4 or 5 factors. As long as I have more than one, this is going to be a composite. And I take each of these numbers in numeric order. So 1, 2, 4. I'm not going to repeat 4 a second time. 8 and 16. And let's look at the very bottom one, 24. This is going to be a big one. So we got 1 times 24. We have 2 times 12. We have 3 times 8. We have 4 times 6, which means 1, 2, 3, 4, 6, 8, 12, and 24 are factors of 24. That means I can multiply this by another number to get me to 24, making this composite. Again, this has 4 factor pairs to equal 24. Doesn't make it any more composite than 16 or 6 that only had 2. It just simply does it have 1 or more. If it has more, then it's composite. If it's only 1 like 7, then it is prime. So on the back side of the page, we look at the kind of factor pairs for each number. So for instance, in this first one, we know we have 1 times 25. 2, nope. 3, nope. 4, nope. But 5, yes. 5 times 5. So this would be a composite, and our factors would be 1, 5, and 25. For 28, 1, 28, 2, and 14. 3 does not go into 28, but 4 goes in 7 times. So it is composite. Factors are 1, 2, 4, 7, 14, and 28. And technically, they wouldn't have to be from smallest to largest, but that is classically what people do. Okay? So you could recognize for 1 and 29 that unfortunately, 1 and 29 is the only factor pair making this prime, with the only factors 1 and 29. If it had any more factor pairs, then it would shift to composite. Down below, I'm just going to rotate this. It says, Brian says all prime numbers are odd numbers. List all of the prime numbers less than 20 in numerical order. So that's what you would do here. And then list to show your Brian's claim is false. And I'll give you a hint. There is one number that proves that all prime numbers are not odd. Okay? Lastly, Sheila has 28 stickers to divide evenly among 3 friends. She thinks there'll be no leftovers. Use what you know about factor pairs to explain if Sheila is correct, right? So she's going to break it into groups of 3, and will there be leftovers or not? That's where you're kind of conquering as you go through this problem.